All right, so the fence-mounted system. We put a processor on the fence. We apply the sensor cable to the fence, and it sends a pulse down that sensor cable. I want you to think of that pulse like a radar signal. Send that radar signal down the sensor cable. When someone interacts with that fence, it reflects that radar pulse back to the processor. So think of it just like a radar system out in the open air, right? An airplane flies by through the radar. If it's a small plane, it sends a small reflection back. If it's a really big plane, it sends a really big reflection back. And not only can you tell the distance to that object, but you can tell the size of it based on that return pulse. Our fence-mounted sensor, the MicroNet system you use, is exactly like that. It sends those radar detection pulses. When you interact with the fence, whether it be wind blowing, whether it be an earthquake, whether it be someone trying to cut through that fence, all of those vibrations are sent back, reflected back to the processor. The really small ones, like wind and vibration from the ground, those are ignored. The big ones, like someone cutting the fence, like someone trying to climb over the fence, those ones are received and they're paid attention to. And the way we differentiate between what's ignored and what's actually paid attention to is by our alarm threshold. So the alarm threshold is independently adjustable for any given cell along the perimeter. But essentially, this is what you get. Someone interacts with the fence, it reflects it back, and you get a location. All right, so this is the breakdown of the sensor cable. Our sensor cable is a 4-conductor copper-based sensor. The middle conductor, this little guy right here, doesn't move. It's solid. It's a copper core surrounded by a dielectric with 2 small keyways cut into that dielectric. Right? These little guys right here are open. And within those openings, there's 2 very small sensor wires placed in there. Those sensor wires move. They can move around. I've actually taken a 100-meter roll of cable and pulled the sensor wire straight out of it. They're free-floating inside there. And the idea here is that when you interact with the cable, these little wires move around inside there. All right? So just outside that, there's a Mylar wrap. The Mylar wrap holds those sensor wires in place, and it isolates them from the tinfoil shielding that's around that. That tinfoil shielding that encapsulates the cable is intended to keep the radar signal inside. Now we use time domain reflectometry, TDR, very fancy words, right? But I call it radar, TDR, same thing. We send information in pulses. Those pulses are reflected back, similar to a radar signal, right? So the only thing that keeps that in is the tinfoil shielding. The tinfoil shielding keeps all electromagnetic interference out and radio frequency interference out. So EMI and RFI are shielded from the sensor, and the radar signal inside is shielded from anything outside. Okay? So outside of that shield, we have a braid, and the braid is what provides your floating ground. So you'll notice that there's not a bunch of ground rods on the fence system. Each processor is not grounded around the perimeter. We only ground the fence-mounted system at 2 locations, and that's where you have power. So where we have the JB70 surge protector come in, that's where we're providing a ground. Once you get about 60 or 70 feet or so away from that processor, that braid provides the ground potential. And by using a floating ground potential on the sensor, we electrically isolate it from the fence structure itself. So these little sensor wires move around inside there. The tinfoil shielding provides EMI RFI protection. The braid provides ground. When you open each of your processors, you'll notice that the sensor cable comes up and is attached flush onto that board. Well, if you move that cable and look, there's actually a braid on the board. And those braids should be flush against each other. If you're checking on your installer and you open one of those processors and you pull that little block off and that braid isn't flush up against the other one, then the installer landed that cable the wrong way. So this is something that anybody should be able to check and view and do a spot check. You should walk out there and there should be dielectric grease. So where the sensor cable comes up and the 2 little sensor wires are out of it, dielectric grease should be from there all the way down the braid, all the way until it hits the outer jacket. And the reason for that is because these little holes are here, water or humidity, moisture can seep in there, right? This cable is a living, breathing thing. When it gets hot outside, it expands, draws air and moisture in. When it gets cold, it contracts and it pushes that out. Well, what can happen if you don't put the dielectric grease on here is it expands and draws humidity in, it contracts and it pushes it further down. So if you have that braid with that dielectric, with a tinfoil shielding, those are two metals touching each other inside the sensor cable. You add moisture to that, and now you're going to get corrosion. So these are things that you can spot check your installers on. You can look and make sure there's dielectric grease going from the outer jacket of the cable all the way up to where the sensor wires are. Because when it does breathe, when it does expand, if they put that dielectric grease on there, it draws that in and it seals itself. Then you don't have to do any maintenance on it for years. Make sense? Okay. So some key benefits of the MicroPoint system, the MicroNet system. Y'all call it MicroNet. MicroNet has metal enclosures. They have lockable boxes, armored cable, metal ties, all these high security functions. Prisons are one part of what I work with, so I might slip up and call it MicroPoint. MicroPoint is our less secure version. They use plastic boxes, not armored cable, plastic zip ties to hold the cable to the fence. It performs the same, but doesn't have all those extra high security features. So our MicroNet system, sensitivity leveling. This is our calibration. When you take a metal object and drag along the fence, it calibrates, okay? It calibrates that cable to that section of fence. Point impact discrimination is our ability to determine a single impact versus a distributed event. These are our marketing buzzwords, very fancy. Point location, be able to pinpoint to within 1 meter. Free format zoning means that you can set zones anywhere independent of hardware. So your cable doesn't have to be a zone. Cable can be 10 zones. The whole perimeter can be 1 zone. It's whatever works for you, not whatever works for the installer. And then, of course, power and data, all is common amongst all our products and is passed along the sensor cable. All right, so this is what a typical system looks like. You've got processors, sensor cable, y'all call them CTUs. In the commercial world, we call them link units. But a CTU is a plastic tube with a long circuit board inside there. If you encounter our products out in the field in a commercial site, the link units will be in the same box, and it's actually a bigger board. Totally different configuration. But those are tampered. So the reason we use CTUs in the prison environment is you can seal them. You can put that potting compound inside there and totally fill and seal those tubes. And then you don't have to worry about tamper issues. You don't have to worry about somebody opening a box and messing with anything in there. So power and data come from the control room, out around the perimeter, back into the control room. We call this the fault tolerant loop. One thing you want to be checking on when you're designing new systems is this fault tolerance. That way, if someone were to cut the cable, shoot a processor, blow up a box, something like that, you still have power and data around the perimeter. This is bidirectional. And you can tie the microwaves in. You guys who have dealt with our microwaves attached to the MicroPoint system, the analog microwaves, the 310s and the 300s, those are 12 volt at very, very low amperage microwaves. Our digital microwaves are 10.5 to 60 volts DC, right? So that means that at 12 volts, they require a much higher amperage. So on the processors themselves, on the power coming in, there's 3 terminals. One says ground, one says V out, one says V in. That's raw power coming into the processor. If you're taking and attaching a digital microwave to one of the processors, use the V out. Don't use the 12 volt regulated voltage that's on the other side of the board. The V out is going to be raw power from the system. The 12 volts is going to be 12 volts at 150 milliamps, and it won't be enough to power the digital microwaves. So just for an FYI, for those of you that are in the field and actually hands on the equipment, if the installer puts it on the 12 volts and they say it's not working, they attach it to the wrong terminal. Make sense? Okay. So you might be wondering what a calibration looks like. We take a metal object, we drag along the fence. As we're dragging along the fence, what we're looking at here, this is the software tool the technicians use to install, calibrate, and tune and adjust the system. On the bottom, this is the distance from the processor in cells of 1.1 meter length. This is a magnitude of events, the strength of those events. This blue line, that's in real-time response to what's happening on the perimeter. And each of these little flat tick marks here represent the strength of an event at that specific cell. Okay? So this is the system learning. This section of cable is attached to this fence panel, And this is what typical vibration looks like on this panel, calibrating it to the system. So you'll notice they're not flat. Some are higher, some are lower. That's a good thing. If your installer comes in and changes this to make it to where it's a flat line, they don't know what they're doing. They did it wrong. You want some to be higher. You want some to be lower. That is a specific response to that section of cable. If a fence is really floppy, if it's loose, if it's like an anti-climb fence, right, where you try to climb up on it and it flops over and makes it difficult, that's going to have a very different response than a fence that has very heavy poles where the fabric is stretched very tight and there's support beams in between it, right? So we want to know what those differences are, and this is how the system does that, by using a calibration. This is when you use the cut simulation tool, the finger, the clicker. You touch it to the fence, you pull it back to the slot, and you let it go. And what you get is a specific response. The MicroPoint fence sensor cable can detect up to a 12-foot fence fabric. So if you have one fabric of fence, you can put that cable on there, and it'll detect cuts like this accurately to within about a 12-foot area, okay? So if you have a 15-foot fence, the events at the very top of that fence, they're going to be much smaller. It's going to be more dampened when the vibration actually gets to the sensor cable. But what you'll see here is that some of these events are lower and some of these events are higher. What we want to do with this during the system installation is bring that sensitivity all the way down. We do like a -20. So we bring it 20 dB lower than the calibration. And then we use that cut simulation tool to ping the fence. And it gives us a response. And this tells us if I were to cut the fence with an average size bolt cutter, this is what the response is going to look like. And so I went to Home Depot and I got a bunch of different sizes. I bought 3 different bolt cutters. And then I called one of my buddies who worked for a towing company, and he brought me his big bolt cutters. And we went out to our test site south of Phoenix in Maricopa in the desert. And I hit with the test tool, and then I went out there and I cut a bunch of our chain link fence. And believe it or not, they're really, really accurate. So the first notch on the cut simulation tool represents really big bolt cutters that you can use a lot of leverage and very gently cut through a chain link fence. That's the first notch. The second notch represents pretty much anything in between that you can buy at a hardware store, an average set of bolt cutters. So if you just go to Home Depot and buy a pair of 18, 12, 20-inch bolt cutters, that's what the middle notch is going to do. And that middle notch is going to look similar to this. All right? They all pretty much look the same. When you start getting into the smaller bolt cutters, that's when it really starts to make a big difference. It's a very strong impact on the fence. It creates a lot of vibration. You're going to have to work to get through the fence. And so this cut tool was designed specifically for that. Small, medium, and large bolt cutters cutting through a chain link style fence. Really accurate. So what we want to do is we want to ping that fence at different locations. This is going to get us a response at each of those locations. And for y'all, you probably want to do this on every single fence panel. If your installer's not using the cut tool on every single fence panel, they're doing you wrong. They're not doing their due diligence. We want to make sure that at a prison facility, anywhere along that perimeter, high, low, middle, corners, sides, anywhere you go with this cut tool, we should be able to detect someone interacting with the fence sensor. So with this system, we'll set 1, 2, 3, or 4 events before an alarm is generated. An event is something that passes that red alarm threshold line. Okay? So we define what that sensitivity is based on using the cut simulation tool. We ping the fence, we get a response, and then we adjust that red line to determine how sensitive we want the system. We can make it really, really, really sensitive by bringing that line way down. But you'll see a cut is going to produce an event that's up here at 75 dB on this system. Our alarm threshold is set down here at 60. So we know we're pretty far above that. Most systems, there's a 6 to maybe 10 dB range from the peak of those cuts to where the actual sensitivity is set. Maybe that. Most are 4 to 6. But there's a balance. As y'all know, anytime you put a sensor out there, there's a chance for nuisance alarms, right? Heavy wind, ice picks up on the fence. In the desert, we have tumbleweeds. Those tumbleweeds can be big. They can be heavy. At some point in time, we will have tumbleweeds stacked 12 to 15 feet high, bunched up against a portion of the fence or against our building when we have the dust storms during our monsoon season. And they're banging against the fence. So you have to have a balance there between sensitivity, number of events before an alarm takes place, and a response, right? Because every time you have an alarm, there's got to be a response to it. So immediate visual verification is key. You have an alarm, camera turns and looks, everybody looks at it and says, all right, nothing's happening there. Well, if that happens 10 times a day at the same space, same spot, if every time you look over there's nothing happening there, what happens? You get complacent. You start ignoring it. Oh, it's that zone 12 again. Ignore that. So we always try to find a balance. So when we're going with new installations, we do this. We ping the fence, we adjust the sensitivity, and then we let it set for a while. And after maybe a season, after maybe some heavy storms, we review, where were my nuisance alarms at? Where did I have an issue? The system will tell you where it's overly sensitive. It'll tell you where the fence has an issue. You just need to pay attention to it. Okay? Does that make sense? Everybody understand that process? It's about managing expectations. If you think it's just going to go in and you're just going to leave it, then you're setting yourself up for failure and frustration. But if you know that it's going to go in and we're going to have to do some tuning over time, then you've got the right expectation there. So once we get the system set up, it's kind of hard to see up there, but we identify portions of the fence with camera views. So I don't know if y'all know any camera guys or not, that maybe be able to get you some perimeter cameras. But if you do, and if you spend some money on them, then you can tune those cameras and you can turn them to presets. You can have the MicroPoint fence-mounted system turn those cameras to presets defined based on cell numbers. So like we showed in that previous video, when you ping the fence, an event pops up. That tells you what cell it is. Those cell identifiers are broken down into zones. And so you have a processor, and the cable goes out. It starts at cell 0, and it works its way up. Your zones are device address, so a processor number, processor 1. It's a cable on the left, from cell 20 to cell 52. And that should be tied to a certain preset. When you look at that zone, the camera view should be greater than the actual zone. Does that make sense? You always want your camera view to overlap. You want the camera, if this is my zone here, I want my camera view to be that. And the reason behind that is, if someone bangs on that fence and then runs, you still want them to be in view by the time that camera's turned and looked at them. By the time the guards look up, or the operators look up at that monitor. You want to be able to see that. So if your zones are really tight, if your camera views are really tight on those zones, you might want to consider backing them up a little bit, widening them a little bit to make sure there's good overlap between there. These are good practices for using the fence or buried systems. And then there's a couple different options, right? So we use relay outputs for one option, and then others we use software integration. So I always try to push relay outputs if at all possible. If you have existing PLCs, that's to me the best way to go. Use relay outputs, time into your PLCs, that just manages everything. You can use your old mobile maps, all those fun things. If you're using the software integration, your head-end device is going to be called an RPM, a remote polling device, or a remote polling module. So the RPM is a small circuit board. It's got a little RJ45 network connection on it, and it's got a USB-A type plug on it. From that device, you can plug in and reach any of the processors on the fence. Okay? So if you're troubleshooting, or if you're trying to find a status of something, if we are troubleshooting with you and we say, hey, pull an event history on one of the processors, you don't have to go all the way out to your perimeter to do that. You go to your control room, plug into the RPM, retrieve that. Same thing if you're using the control module, the CM2. From the CM2, you can plug into that and retrieve anything from any of the processors on the fence as well. So just to show you some pictures of some different applications, the fence sensor, this can be installed on all different types of mediums, if you want to call it that, right? Razor coil, we can put it directly on Razor. The armored version is intended to be installed specifically for Razor. You can slice and dice and cut that outer jacket, and it's got we use, I think now, a brass braid that's inside it to arm and protect the inner core. And so the armored cable is our standard sensor cable with an armor wrapped around that and then a second outer jacket. And the idea there is that it can be installed on those different materials and can be cut, but it's still weather resistant and weatherproof. It's still pretty easy to cut through those cables, armored or not. But you can cut the outer jacket with the razor coil, barbed wire, anything like that, and it won't affect sensor performance.